These are a section of questions where you were asked to read the information before, and you've all got that in your books. Describe the bonding between carbon atoms in diamond. Include a dot cross diagram in your answer. Each carbon atom has 4 bonds. So each carbon has 4 free electrons and it bonds to 4 other carbon atoms. Unlike graphite, that only bonds to 3. Each carbon atom has a shared electron between the 3 other carbons. So as you can see here, they're bonding to another carbon, and this carries on and on and on. Okay, explain why graphite is a good conductor of electricity. 3 electrons can conduct electricity. 3 electrons used to form the covalent bond. So carbon's got 4 bonds. 3 of them are used to form the covalent bond. 1 of them is free then to move and conduct electricity. Explain why graphite is soft and slippery and can be used as a lubricant. Layers which can slide over each other because of the weak forces in the adjacent layers. So the layers have got weak forces in them. That means the layers can slide, which means it's a lubricant. Diamond is a very dense allotrope of carbon because the carbon atoms are tightly packed. Calculate the volume of the cube containing carbon atoms in diagram 2. In diagram 2, they give you the length, the height and the width. You've just got to times them all together. Round it up properly, you should have got 0.047 nanometers cubed. So again, this gives you information about the Olympic Games and a table with tensile strength, density and melting point. It says state which material is most suitable for use in racing bikes, giving 2 reasons for your answer. Carbon fibre, high tensile strength and a low density, light for racing but also really strong. Sodium reacts with oxygen to give sodium oxide. Using the electron structure below, draw a dot and cross diagram. Sodium's a metal, oxygen's a non-metal, so it's ionic bonding. They've given you the outer shells. You're going to need 2 sodiums because oxygen's got 6. They're going to transfer their electrons over, and then you're going to put your ion charge. Look at that, it's 3 marks, okay? So we've got to get good at doing this. Sodium ion then, so once it's lost its electron, 1 sodium ion is going to lose 1 electron, so it's 2, 8. 1 oxide ion is going to have gained 2. Name the structure present in ammonia, NH3, so they're both non-metals, and explain why ammonia has a low melting point. It's covalent bonding. They share electrons, less energy required to break the bonds. So, nice easy question there. Magnesium reacts with chlorine to form magnesium chloride. The following diagram represents the electron structures of magnesium chloride atoms. So they transfer electrons over. Be careful that you do that even though there's no line, and make sure you transfer 1 to each chlorine. Complete the table using the information of the electron structures of magnesium and chloride ions. So magnesium has lost these 2, so it's now 2, 8. 1 chlorine atom has gained 1, so it's negative 1. Chlorine gas consists of 2 chlorine atoms bonded together. Draw a diagram in the box to show how the atoms bond to form the chlorine molecule. So they covalently bond, they share these electrons in the share zone. You could draw it bigger than that. Name the type of bonding this is. It's covalent bond. If a 6 marker comes up in this topic, it's likely to be drawing out covalent or ionic bonding. So lithium chloride, a metal and a non-metal, is a solid with a high melting point. It conducts electricity only when molten or in solution. Describe the bonding present. You may wish to, so when they're saying you may wish to include a diagram, they've given you the electron structures. So lithium, it's got 1 in its outer shell, chlorine's got 7. Draw the 1 going over here and the formation of their ions. Lithium has lost 1, so it's positive. Chlorine has gained 1, so it's negative. Then describe the bonding. Lithium chloride is ionic bonding. Electrons are transferred between a metal and a non-metal. This creates an electrostatic force which requires a lot of energy to break, hence the high melting and boiling point. Lithium chloride can only conduct electricity when molten because the ions are free to move, so the can transfer electrons. Another type of 6 marker you might see, using water and carbon dioxide examples, explain what is meant by covalent bonding. So can you see that the 6 markers are normally about the bonding? Why some molecules contain double bonds, you may wish to use diagrams in your answers. So I used water, which is a single bond, 2 hydrogens on either side bonding to the spare electrons and oxygen, and then carbon dioxide, which we talked about, has got double bonds, so they share 4 instead of 2. Covalent bonds are when non-metals share electrons, which results in weak bonds with low melting and boiling points. Some molecules contain 2 bonds as they have 4 electrons being shared, example, carbon dioxide. This results in 2 bonds in the same place, a double bond. Another example then of ionic bonding, calcium transfers its 2 electrons to oxygen. Calcium's 2+, oxygen's 2-. This question comes up an awful lot. Explain why both compounds have high melting points and why the melting point of calcium oxide is higher. Higher charges, so calcium's got a +2 and a -2, so there's a stronger force between them than in sodium chloride, which is a +1 and a -1. This means electrostatic charge is larger, so it requires more energy to break. There's a higher charge between them two. Graphene and graphite are different forms of carbon, so they're allotropes of carbon. Explain why the bonding present in both forms makes them good conductors of electricity. They have 3 carbon bonds with a free electron. So carbon's got 4 free electrons in its outer shell. With these 2 compounds, they have 3 carbon bonds, so 3 carbons bonded to other carbons, and then 1 free electron, which means electricity can be conducted across the compound. Another type of 6 mark you might see, describe what is meant by smart material. Use thermochromic and photochromic materials to support your answer, given everyday uses of each. Smart materials are materials which change structure and react to a change in their environment. Thermochromic materials react to a change in temperature, often change in colour. Forehead thermometers, the cups when you put hot water in them. Photochromic materials react to a change in light. This is seen in sunglasses, glasses, which change colour when exposed to light, so they become sunglasses or glasses. Nanosilver particles can be used in socks, plasters and disinfectant sprays. Explain why nanosilver is suitable for the use in these examples and state why some people are concerned about the use of nanoparticles in everyday life. Nanosilver has antibacterial and antifungal properties, which is why it's used in socks and plasters. We don't know the long-term effect of nanoparticles. Copper and titanium are important metals. The following table shows some of their uses. Copper, electrical wiring, water pipes, saucepans, jewellery. Titanium, hip replacements, rotors on helicopters, pipes in electrical industry. Describe how the properties of copper and titanium make them suitable for these uses. Copper is a good conductor of electricity due to its free electrons. They are also good conductors of heat, which is why they're used in wiring and pans. Copper is also malleable due to the electrons being able to slide, so it can be moulded into shape for jewellery and pipes. Titanium is unreactive, so it can be used in chemical pipes. It is also malleable and ductile, which is why it's used in hip replacements and rotors. Smart materials are used to make frames and lenses for certain spectacles. Give the name of each type of smart material used and describe the unusual property each. So frames, shape memory alloy can be heated and returned to original shape. You can see there they're bending. Lenses, photochromic lenses, change colour, become sunglasses when exposed to light. Titanium dioxide can be used in sunglasses, sun creams for decades. Sun creams available today use nanoscale titanium dioxide particles. Some people believe using sun creams containing nanoparticles is unsafe. Give the advantage of using nanoscale titanium dioxide particles rather than larger titanium dioxide particles to make sunscreens. Larger surface area have different properties. Explain why some people are concerned about the use of nanoscale titanium dioxide particles in sun cream. We don't know the long-term effects, can get into water and blood. Approximately how many times bigger are common titanium dioxide particles than nanoscale titanium dioxide particles? So just divide them by each other and you should have got 1,200, which was the answer.